In this short video, the following topics will be discussed: reaction rates, the collision theory and activation energy, factors affecting reaction rates, rate laws and reaction mechanisms, reversible reactions and equilibrium, factors affecting equilibrium and equilibrium constants, solubility equilibrium, the solubility product constant, the common ion effect, and how to predict precipitates, free energy and entropy, spontaneous and non-spontaneous reactions. Rate is a measure of how much something changes in a given amount of time. The rate of a chemical reaction is usually given as the change in the amount of reactant or product over time. Example: a piece of iron has a mass of 55.8 grams, which is equivalent to 1 mole of iron. If 1/2 of the iron turns to rust in 1 year, then the rate at which the iron rusts is equal to 0.5 moles per year. Iron rusting is a chemical reaction with a slow reaction rate. In contrast, the burning of wood is a chemical reaction with a fast reaction rate. Consider a reaction where reactants A and Bx form the products B plus Xa. We can already anticipate that, if the reactants do not have enough kinetic energy, the reaction will not happen. Moreover, if the reactants collide at the wrong angle, the reaction will not happen either. An effective collision occurs only if the reactants collide at the correct angle and have enough kinetic energy. Then the reaction will happen. The collision theory is a model that explains that reactants can form products if they collide with enough kinetic energy. The collision theory is used to relate kinetic energy and reaction rates. Let's have a look at the reaction of oxygen gas and hydrogen gas to form water. No reaction will occur if the kinetic energy of the colliding gas molecules is insufficient. The minimum energy that colliding particles need to react is called the activation energy. An activated complex is an unstable arrangement of atoms that exists at the top of the activation energy barrier. Activation energy is a barrier that reactants must cross before products can form. The activation energy barrier must be crossed before reactants are changed to products. In an exothermic reaction, like the formation of water from hydrogen and oxygen, heat is released by the system. In an endothermic reaction, like the decomposition of water, heat is absorbed by the system. An activated complex is an unstable arrangement of atoms that exists at the top of the activation energy barrier. Several factors affect the reaction rates. The first factor is temperature. At higher temperature, particles move faster and collide more often, and more of the particles have enough kinetic energy to get over the activation energy barrier. So, raising the temperature usually speeds up a reaction. What is the effect of concentration on the reaction rate? In air, a light splint glows and soon goes out. The oxygen concentration is too low to keep the reaction going. However, when a glowing splint is placed in pure oxygen, the splint bursts into flame. The increased concentration of oxygen speeds up the reaction. The total surface area of a solid or liquid reactant affects the rate of a reaction. The greater the surface area, the faster the reaction rate, since collisions take place at the surface of reactants. Consider the reaction of magnesium with hydrochloric acid to form magnesium ions and hydrogen gas. Dividing the metal into smaller pieces increases the surface area and the reaction rate. Another way to increase the surface area of solids is to dissolve them. In a solution, particles are separated, so more of them are able to collide with other reactants. Increasing the temperature is not always the best way to increase the rate of a reaction. A catalyst is often better. A catalyst lowers the activation energy, so that more particles have enough energy for a successful collision. Consider the decomposition of hydrogen peroxide. At room temperature, the rate of reaction is very small. From the graph, it can be noticed that the activation energy is much lower with a platinum catalyst, which increases the rate of the reaction. When the energy barrier is lower, more of the reactant particles have enough energy to form products. As we have seen before, concentration is one factor that can affect the rate of a reaction. Consider the reaction with one reactant A and one product B. The rate at which A forms B can be expressed as a change of A over time. This expression is a rate law, which is an expression for the rate of a reaction in terms of the concentration of reactants. For this reaction, the rate is proportional to the concentration of reactant A. Initially, the concentration of A is high, so the rate is high. As the reaction proceeds, the concentration of reactant A decreases, so the rate is decreased as well. Most reactions have more than one reactant. We must make sure that the rate law includes all the reactants that influence the reaction rate. A chemical equation only tells what reactants are present at the start of a reaction and what products are present at the end. Most reactions are made up of many small steps. The series of steps that take place during a complex chemical reaction is called the reaction mechanism. The graph for a multi-step reaction has a peak for each activated complex and a valley for each intermediate. This reaction has 4 steps, and the products of the first 3 steps are intermediates. An intermediate is a substance that is a product in one step of a reaction mechanism, and a reactant in the next step. In a multi-step reaction, the steps do not all happen at the same rate. One step will be slower than the others, which is the rate-determining step. Not all chemical reactions happen in one direction. Some reactions are reversible. A reversible reaction is a reaction in which reactants change to products, and products change back to reactants at the same time. The reaction of sulfur dioxide reacting with oxygen to form sulfur trioxide is a reversible reaction. The reaction from left to right is called the forward reaction. The reaction from right to left is called the reverse reaction. The two equations can be combined, as shown with a double arrow, which represents a reversible reaction. When sulfur dioxide and oxygen are mixed in a sealed container, the forward reaction begins. The rate of the reverse reaction is equal to 0 initially, since no sulfur trioxide is present. Once sulfur trioxide forms, the reverse reaction begins, and as more sulfur trioxide forms, the reverse reaction speeds up. At the same time, the forward reaction is slowing down, because sulfur dioxide and oxygen are being used up. At some point in time, the rate of the forward reaction will be equal to the rate of the reverse reaction, and this state is called chemical equilibrium. The constant amounts of sulfur trioxide, sulfur dioxide, and oxygen at equilibrium does not mean that both reactions have stopped. Chemical equilibrium is dynamic, so the reactions continue to take place. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. At equilibrium, the relative concentration of the reactants and products are the equilibrium position of a reaction. Example, if reactant A forms product B, and the equilibrium mixture is 1% reactant A and 99% product B, we write it in this way. Changing one or more conditions of the reactions can upset the chemical equilibrium. When a change in conditions happens, the system adjusts to go to a new equilibrium. The new equilibrium position will be different from the original equilibrium position. This is called a shift in equilibrium. The French chemist Le Chatelier studied the factors that affect equilibrium, and it is known as Le Chatelier's principle. Le Chatelier's principle states that an equilibrium system will shift in a way that reduces the stress on the system. Conditions that can stress a system include changes in concentration, changes in temperature, changes in pressure. Let's illustrate the effect of concentration with the decomposition of carbonic acid in aqueous solution. First, let's add carbon dioxide. Because carbon dioxide is used up in the reverse reaction speeds up. As more carbonic acid is formed, the forward reaction also speeds up. In time, the rates of the forward and reverse reactions become equal. Equilibrium is restored with a different equilibrium position. In other words, the equilibrium concentration of the reactants will be higher than before. Conclusion: adding product shifts the reaction in the direction of the reactants. Now let's remove carbon dioxide. A decrease in carbon dioxide concentration causes the reverse reaction to slow down. As less carbonic acid is formed, the forward reaction also slows down. In time, the rates of the forward and reverse reactions become equal. Equilibrium is restored with a different equilibrium position. The equilibrium concentration of the reactant will be lower than before. Conclusion: removing product shifts the reaction in the direction of the products. Let's have a look at the effect of pressure in chemical reactions with gases. Consider the following case. Nitrogen gas and hydrogen gas can react to form ammonia gas in a reversible reaction. In the initial equilibrium, there are 5 molecules of hydrogen, 2 molecules of nitrogen, and 4 molecules of ammonia in a sealed container. To disturb the equilibrium, we will increase the pressure, or reduce the volume, by pushing the plunger. After some time, a new equilibrium will be reached, with less molecules of reactants, and an increased number of product molecules. Pressure is related to the number of gas molecules. The forward reaction can reduce the number of particles, so the reaction will shift toward products. To determine the effect of pressure on an equilibrium with gases, we are going to use a trick. Put the pressure symbol on the side with the largest number of molecules. In this case, P should be put on the reactant side. If P is on the reactant side, the forward reaction can reduce the pressure. If P is on the product side, the reverse reaction can reduce the pressure. The effect of volume on equilibrium can be explained using the effect of pressure. An increase in volume has the same effect as a decrease in pressure, and a decrease in volume has the same effect as an increase in pressure. Let's do an exercise. Consider the equilibrium reaction between nitrogen and oxygen to form nitric oxide gas. What is the effect of pressure on this equilibrium? Pause the video now to think about your answer. The pressure has no effect on this equilibrium for this reaction. Conclusion: if the number of reactant gas molecules is equal to the number of product gas molecules, then changing the pressure has no effect on the equilibrium. Temperature or heat also affects the equilibrium. Colorless dinitrogen tetroxide and brown nitrogen dioxide exist in equilibrium. The balanced equation is shown. The reverse reaction produces heat. When adding heat, the temperature rises, and the equilibrium shifts toward nitrogen dioxide, and the mixture is darker. Removing heat by cooling reduces stress, and the reverse reaction is favored. Catalysts reduce the time needed to get to equilibrium. Catalysts do not affect the concentrations of reactants and products at equilibrium. Remember, equilibrium is reached when the concentrations don't change anymore, they remain constant. When a sealed container is filled with nitrogen and hydrogen, ammonia starts to form. The chart shows the decrease in reactants and increase in product, until equilibrium is reached. The dotted lines show the concentration versus time without catalyst. The solid lines show the concentration versus time when catalyst is present. The concentrations at equilibrium remain the same, but the time needed to get to equilibrium is reduced. The equilibrium position is expressed as a number, which is called the equilibrium constant. The equilibrium constant is equal to the ratio of product concentrations to reactant concentrations at equilibrium. The numbers A, B, C, and D stand for the number of moles. A large value of the equilibrium constant tells us that the equilibrium mixture will be mostly product. A small value of the equilibrium mixture tells us that the equilibrium mixture will be mostly reactant. Important remark: the value of the equilibrium constant depends on the temperature. When dinitrogen tetroxide decomposes, it breaks down into nitrogen dioxide gas, represented by this chemical equation. The equation for the equilibrium constant is shown as well. When the temperature rises, the equilibrium shifts toward nitrogen dioxide. So, the value of the equilibrium constant will be larger at higher temperatures for this equilibrium reaction. Scientists use the solubility product constant to compare solubilities of ionic compounds. Consider ionic compound A dissolving in water to produce ions C and D. The exponents C and D are the coefficients of ion C and ion D from the balanced chemical equation. C and D are the concentrations of the dissolved ions. As an example, here is the solubility constant for silver chloride, which is only slightly soluble in water. The smaller the value of the solubility product constant, the lower the solubility of a compound. Compare the solubility product constants for silver chloride and silver bromide. Since the value of the solubility product constant for silver chloride is higher than for silver bromide, silver chloride is more soluble than silver bromide. A common ion is an ion that is found in more than one ionic compound in a solution. The common ion effect is the lowering solubility of an ionic compound due to the addition of a common ion. Lead chromate is considered very poorly soluble in water. The equilibrium reaction is shown with the value of the solubility product constant. In the left figure, we have a saturated solution of lead chromate. The yellow solid is lead chromate. When lead nitrate, which is soluble in water, is added to the saturated solution of lead chromate, it increases the rate of the reverse reaction. In other words, adding product, lead ions in this case, to a system at equilibrium, causes a shift toward reactants. The solubility product constant can be used to predict whether a precipitate will form when two solutions are mixed. We will illustrate this with an example. Barium sulfate has a very low water solubility. If the product of barium ion concentration times sulfate ion concentration is larger than the solubility product constant, then a precipitate will form. If the product of barium ion concentration times sulfate ion concentration is smaller than the solubility product constant, then no precipitate will form. Let's mix 0.5 liter of a 0.002 molar barium nitrate solution with 0.5 liter of a 0.008 molar sodium sulfate solution. The total volume after mixing is 1 liter. After some simple calculations, we find that the barium ion concentration is equal to 0.001 moles per liter. The sulfate ion concentration is equal to 0.004 moles per liter. So, the product of the concentrations of the ions is larger than the solubility product constant of barium sulfate, so a precipitate will form, as shown in the picture. Some of the energy released in a chemical reaction can be used to do work. Energy can be obtained from a chemical reaction only if the reaction happens. Reactions can be divided into two groups based on whether they tend to occur. Spontaneous reactions, reactions that favor the formation of products. These reactions release free energy. Nonspontaneous reactions, reactions that don't favor the formation of products. Some spontaneous reactions are so slow that they appear to be non-spontaneous. The reaction of table sugar and oxygen is an example. At room temperature, it would take thousands of years for this reaction to reach completion. A reaction that is non-spontaneous in one set of conditions may become spontaneous in other conditions. Example: photosynthesis in plants cannot happen without sunlight energy. Spontaneous reactions produce large amounts of product and release free energy. Although melting of ice is an endothermic process, it's spontaneous. Why is that? The explanation is that the enthalpy change is not the only factor that makes it spontaneous or not. The other factor is disorder, which is also known by the scientific name entropy. Liquid water has a higher degree of disorder than ice, and that's why melting of ice is spontaneous. Entropy is a measure of the disorder of a system. The symbol for entropy is capital letter S. The law of disorder is the natural tendency for systems to move in the direction of increasing disorder. Let's illustrate this with an example. Look at the sealed container that has two compartments separated by a lid. One compartment contains gas molecules. The second compartment is vacuum. When we remove the lid, gas molecules will spread over both compartments, leading to more disorder, which translates in a higher entropy value. Here are 4 ways to increase the entropy. 1. Phase changes. A gas has more entropy than a liquid or a solid. A solid has less entropy than a liquid. 2. Divide a substance into parts, like when a hammer breaks an object into pieces. Entropy also increases when solids form solutions. 3. Entropy tends to increase in chemical reactions when the total number of product molecules is greater than the total number of reactant molecules. 4. As the temperature increases, particles gain energy and are able to move faster, which leads to more disorder. In every chemical reaction, heat is either released or absorbed, which results in a change in enthalpy, and the entropy either decreases or increases. Enthalpy change and entropy change are the 2 factors that determine whether a chemical reaction is spontaneous or not. These 2 factors are combined in the Gibbs free energy equation, as shown here. Delta G is the change in Gibbs free energy, delta H is the change in enthalpy, and T times delta S is the change in entropy, multiplied by the temperature in Kelvin. For a spontaneous reaction, the change in free energy must be negative. If the change in free energy is positive, the reaction is non-spontaneous. Exothermic reactions with an increase in entropy are always spontaneous. Endothermic reactions with a decrease in entropy are always non-spontaneous. Exercise. In the reversible reaction for the formation of ammonia, also known as the Haber process, the enthalpy change favors the forward reaction, but the entropy change favors the reverse reaction. Question: what are 3 things that can be done to increase the % yield of your product? Pause the video now to think about your answer. 1. Increase pressure, since 4 molecules of reactants form 2 molecules of product. 2. Remove heat, cool down the reaction mixture. 3. Remove ammonia.